On July 1st, 2025, at exactly 2:37 a.m. local time, a robotic telescope in Chile's Atacama Desert captured something that would rewrite astronomy textbooks. The ATLAS survey system, designed to hunt for dangerous asteroids, detected a faint dot moving against the star field. Within hours, this unremarkable speck of light had astronomers around the world abandoning their planned observations and pointing every available telescope toward the southern sky. The dot had a name by morning: 3I/ATLAS. The I designation marked it as something extraordinary, an interstellar visitor, only the third confirmed object from beyond our solar system to grace our cosmic neighborhood. But this wasn't just any cosmic tourist. This visitor was moving at impossible speeds, over 130,000 miles per hour, carrying the momentum of an entirely different star system. Initial calculations revealed something both thrilling and terrifying. Unlike the asteroids and comets that call our solar system home, 3I/ATLAS was following a hyperbolic trajectory, a path that would carry it through our stellar neighborhood and back into the galactic wilderness, never to return. We had one chance to study this messenger from the stars, and that chance was measured in months, not years. The discovery triggered a cascade of questions that rippled through the scientific community. Where had this visitor come from? What secrets might it carry about alien worlds and distant suns? Most immediately pressing of all, how close would it get to Earth? The mathematics of orbital mechanics are unforgiving. Every object in space follows predictable paths determined by gravity and velocity. Within days of discovery, computers at NASA's Jet Propulsion Laboratory were crunching numbers that would determine whether humanity was about to witness a cosmic spectacle or face an existential threat. The preliminary calculations suggested 3I/ATLAS would pass relatively close to Earth, close enough for detailed study, but the exact distance remained uncertain. As more telescopes tracked the visitor's path, refining measurements with each observation, a picture began to emerge. This wasn't going to be a distant flyby that left us straining to glimpse details, nor was it going to be a terrifyingly close encounter that sent governments scrambling for emergency protocols. Instead, 3I/ATLAS was threading the needle with almost surgical precision. Its path would carry it through the inner solar system at a distance that seemed almost designed for optimal scientific observation. Close enough to reveal its secrets, far enough to ensure our safety. But that perfect positioning raised uncomfortable questions. In a universe where cosmic encounters are typically matters of random chance, why was this visitor arriving with such convenient geometry? The coincidence felt almost too perfect, as if someone or something had calculated this trajectory with Earth's telescopes in mind. As July turned to August, and the first detailed observations began streaming back from our most sophisticated instruments, one thing became crystal clear. 3I/ATLAS wasn't going to give up its secrets easily. Every measurement revealed new mysteries. Every observation raised fresh questions about what interstellar visitors should look like. The stage was set for a cosmic drama that would unfold over the coming months. A race between human curiosity and cosmic timing, with the visitor's closest approach serving as the climactic moment when all mysteries would finally be resolved. But first, we needed to understand exactly what close means when dealing with objects racing between the stars. Understanding distance in space requires abandoning everything you think you know about proximity on Earth. When astronomers say something is close in cosmic terms, they're working with a scale so vast that human intuition simply breaks down. The nearest star to our Sun, Proxima Centauri, sits 4.2 light-years away, a distance so enormous that light itself, the fastest thing in the universe, takes over 4 years to cross it. Yet, within our solar system, distance takes on more familiar proportions. The space between Earth and our Moon, roughly 240,000 miles, represents humanity's farthest travels. Mars, our planetary neighbor, swings between 35 million and 250 million miles from Earth, depending on where both planets sit in their orbits. These numbers feel manageable, even if they dwarf earthly distances. When 3I/ATLAS entered our solar system, it brought with it the perspective-bending reality of interstellar space. This visitor had traveled distances measured in light years, crossing the void between star systems over millions of years. By the time it reached our cosmic doorstep, concepts like near and far had taken on entirely new meanings. The challenge facing astronomers wasn't just calculating how close 3I/ATLAS would get to Earth. It was communicating that distance in ways the human mind could grasp. Space agencies learned this lesson the hard way during previous asteroid scares, when technical measurements confused rather than informed public understanding. Astronomical units provide the standard measuring stick for solar system distances. 1 AU equals the average distance from Earth to the Sun, roughly 93 million miles. It's a convenient unit because it makes planetary distances more manageable. Mars orbits at about 1.5 astronomical units from the Sun, Jupiter at 5.2 astronomical units, and Neptune at a distant 30 astronomical units. But even astronomical units can mislead when discussing cosmic encounters. An asteroid passing at 0.1 astronomical unit, about 10 million miles, sounds safely distant until you realize that's closer than Venus ever gets to Earth. Context matters enormously when dealing with objects moving at interstellar velocities. The key distinction lies between gravitational influence and physical proximity. Objects can pass relatively close in space without posing any threat, because the vast emptiness between celestial bodies creates enormous safety margins. Even our own moon, which appears large enough to cover the Sun during eclipses, sits far enough away that all the other planets in our solar system could fit in the gap between Earth and lunar orbit. 3I/ATLAS brought additional complexity to distance calculations because of its extreme velocity. Unlike asteroids that creep through the inner solar system at modest speeds, this visitor was racing through our neighborhood at velocities that compressed normal timing relationships. The difference between a safe passage and a concerning approach might be measured in hours rather than years. The psychological aspect of cosmic distances creates its own challenges. Humans evolved to assess threats and opportunities within walking distance. Our nervous systems activate fight or flight responses for dangers measured in meters, not millions of miles. When dealing with objects in space, this ancestral programming works against clear thinking. Media coverage of asteroid approaches often struggles with this disconnect between cosmic and human scales. Headlines about close encounters trigger anxiety about impacts, even when the actual distances involved provide comfortable safety margins. The challenge becomes presenting astronomical facts in ways that inform rather than alarm. As August 2025 progressed and more precise measurements refined 3I/ATLAS's trajectory, astronomers faced the delicate task of explaining what the visitor's approach would mean for Earth. The numbers told a story of cosmic choreography, an interstellar object threading through our solar system with precision that seemed almost intentionally calculated for optimal observation. Earth's history reads like a cosmic shooting gallery, punctuated by encounters that remind us how dynamic and occasionally dangerous our celestial neighborhood can be. These past events provide crucial context for understanding what constitutes a genuinely threatening approach versus a merely spectacular cosmic show. The Tunguska event of 1908 offers perhaps the most sobering reminder of what too close actually means. On June 30th, something, likely a small asteroid or comet fragment, exploded in the atmosphere above Siberia with the force of several hundred atomic bombs. The blast flattened 2,000 square kilometers of forest and would have devastated any major city. Yet the object that caused this destruction was probably no larger than a school bus. More recently, the Chelyabinsk meteor of 2013 demonstrated how even smaller objects can create dramatic effects. This apartment building-sized asteroid exploded over Russia with enough force to shatter windows across multiple cities and injure over 1,000 people. The event was captured on countless dashboard cameras, providing stark visual evidence of how quickly cosmic encounters can turn from curiosity to crisis. These impact events share common characteristics that distinguish them from harmless flybys. Most importantly, they involved objects actually entering Earth's atmosphere, crossing that crucial boundary between passing nearby and direct encounter. The difference between these scenarios and a safe approach is measured not in millions of miles, but in whether an object's trajectory intersects our planet's physical location in space. The asteroid Apophis offers a more recent example of how distance calculations can evolve. Initially discovered in 2004, this 370-meter wide space rock triggered genuine concern when early calculations suggested a small but meaningful probability of Earth impact during its 2029 approach. The asteroid earned a brief moment of notoriety as scientists worked to refine its orbital path. Subsequent observations eliminated the impact threat, but Apophis will still provide a spectacular show when it passes just 31,000 kilometers from Earth in 2029, closer than many satellites. This encounter perfectly illustrates the difference between astronomically close and actually dangerous. Close enough for amateur astronomers to spot with backyard telescopes, far enough to pose no threat whatsoever. The distinction becomes even clearer when considering larger asteroids that maintain safe distances. The potentially hazardous asteroid 4179 Tutatis regularly approaches within a few million kilometers of Earth, close enough for radar observations to map its irregular shape in detail, distant enough that it never threatens impact. These encounters have provided valuable science while maintaining comfortable safety margins. Near-Earth objects follow a classification system that reflects these distance relationships. Objects that can approach within 7.5 million kilometers earn the designation potentially hazardous, not because they will necessarily impact Earth, but because their orbits bring them close enough to warrant monitoring. Most of these objects pose no immediate threat, but their paths can change over long timescales due to gravitational perturbations. The key insight from studying these cosmic encounters is that genuinely threatening approaches are rare, while harmless but scientifically valuable close passes happen regularly. Our planet sits in a cosmic environment filled with small debris, but the vast majority passes by at safe distances or burns up harmlessly in our protective atmosphere. When astronomers first detected 3 I/ATLAS racing toward our solar system, these historical precedents provided the framework for assessment. The visitor's interstellar origin and extreme velocity marked it as unlike any previous Earth encounter. But the same mathematical principles would determine whether its approach constituted cosmic spectacle or cause for concern. Early trajectory calculations suggested something unprecedented, an interstellar visitor that would pass close enough for detailed study while maintaining distances that eliminated any possibility of atmospheric entry. If these preliminary numbers held true, 3 I/ATLAS would provide the best of both worlds: scientific opportunity without existential anxiety. But confirmation required more precise measurements, more refined calculations, and more time for computers to solve the complex orbital mechanics that would determine exactly how close this messenger from the stars would actually get. The mathematics of orbital mechanics operate with the cold precision of natural law, indifferent to human hopes or fears. When 3 I/ATLAS appeared in our telescopes, computers began calculating its future path using equations that have governed celestial motion since Newton first described gravity's universal influence. These calculations would determine whether Earth faced a cosmic crisis or received an unprecedented scientific gift. Tracking objects through space requires solving what mathematicians call the n-body problem, accounting for gravitational influences from every significant mass in the solar system. While two objects in space follow predictable elliptical orbits around each other, adding a third body creates complexity that can only be solved through computational approximation. 3 I/ATLAS faced gravitational tugs from the Sun, Jupiter, Saturn, and every other planetary mass as it raced through our neighborhood. The initial position measurements came from multiple telescopes, each observation adding precision to the trajectory calculation. Like triangulating a position using landmarks, astronomers combined sightings from different locations to determine exactly where 3I/ATLAS was at any given moment. These positional fixes, accumulated over days and weeks, allowed computers to project the visitor's future path with increasing accuracy. The breakthrough came during the third week of July 2025, when enough observations had accumulated to produce reliable predictions. The numbers emerging from NASA's Jet Propulsion Laboratory painted a picture of cosmic choreography that seemed almost too perfect to believe. 3I/ATLAS would approach no closer than 1.8 astronomical units from Earth, roughly 167 million miles, or nearly twice the distance from our planet to the Sun. This measurement represented a cosmic sweet spot that satisfied every criterion for ideal scientific observation. Close enough that our most powerful telescopes could resolve details invisible at greater distances, yet far enough to eliminate any possibility of gravitational disturbance or atmospheric entry. The margin was so comfortable that 3I/ATLAS could have been 10 times larger and still posed no threat whatsoever. The relief within the scientific community was palpable, but it quickly gave way to excitement about the research opportunities this safe approach would provide. Unlike previous asteroid encounters that required balancing scientific curiosity against potential danger, 3I/ATLAS offered pure discovery potential without existential anxiety. Confirmation of the safe trajectory came through independent calculations performed by observatories worldwide. The European Space Agency's tracking stations, China's Purple Mountain Observatory, and amateur astronomy networks all arrived at nearly identical predictions. When multiple independent analyses converge on the same result, confidence in the mathematics reaches near certainty. The timing of closest approach was predicted with equal precision. Late December 2025, when 3I/ATLAS would reach the point in its trajectory that brought it nearest to Earth's orbital path. By then, the visitor would already be racing away from the Sun, heading back toward interstellar space with velocity unchanged by its brief passage through our cosmic neighborhood. Perhaps most remarkably, the calculations revealed that this closest approach would occur when Earth and 3I/ATLAS were positioned for optimal viewing geometry. Rather than requiring telescopes to peer through atmospheric distortion near the horizon, the visitor would appear high in the pre-dawn sky, perfectly positioned for extended observation sessions. The mathematical precision of these predictions reflects centuries of advancement in celestial mechanics. The same equations that guided Apollo missions to the Moon and hurled Voyager probes toward the outer planets worked flawlessly when applied to this visitor from another star system. Universal physical laws operated identically, whether dealing with familiar solar system objects or exotic interstellar wanderers. The 1.8 astronomical unit minimum distance became the number that defined every subsequent observation plan. Telescope schedules were adjusted, spacecraft missions were redirected, and international collaborations were forged around the certainty that 3I/ATLAS would provide months of safe, detailed study opportunities. But the mathematics that calmed initial fears about Earth's safety also revealed deeper mysteries about the visitor itself. An object maintaining such precise trajectory through multiple gravitational influences suggested either remarkable cosmic coincidence or properties that exceeded current theoretical understanding. The numbers had answered the most pressing question about 3I/ATLAS. It posed no threat to our world. Now those same mathematical tools would be turned toward solving the more intriguing mystery. What exactly was this visitor, and why did its behavior seem so perfectly calibrated for human observation? Numbers alone cannot capture the true meaning of distance in space. When astronomers announced that 3I/ATLAS would approach no closer than 1.8 astronomical units from Earth, the measurement required translation into terms that human minds could actually grasp. This distance, roughly 167 million miles, represented a cosmic sweet spot that would prove perfect for both safety and science. To understand what 1.8 astronomical units means, imagine shrinking our solar system to a scale where Earth becomes a marble. At this scale, the Sun would be a basketball positioned about 26 yards away, roughly the length of a basketball court. The Moon would be a peppercorn circling the marble at a distance of just over 2 feet. Mars, at its closest approach, would be another marble positioned about 40 yards from our Earth marble. In this scaled-down solar system, 3I/ATLAS at its closest approach would pass at a distance of roughly 47 yards from the Earth marble. Close enough to observe clearly, far enough to pose no collision risk whatsoever. The visitor would zip through our miniature solar system at a scale speed equivalent to several miles per hour, fast enough to complete its passage in a matter of minutes. The actual numbers are staggering. 167 million miles represents a distance that light itself, traveling at 186,000 miles per second, takes about 15 minutes to cross. This is the one-way communication delay that mission controllers experience when sending commands to spacecraft exploring the outer solar system. Messages to 3I/ATLAS would take a quarter hour to arrive, and responses would take another quarter hour to return. For comparison, this distance exceeds the gap between Earth and Mars at their closest approach, when the red planet sits roughly 35 million miles away. The 3I/ATLAS flyby distance is nearly 5 times larger than even that relatively comfortable interplanetary separation. In practical terms, our visitor would pass farther from Earth than Mars ever gets during its most distant oppositions. The safety margin becomes even more apparent when considering Earth's gravitational influence. Our planet's gravity well, the region where Earth's gravitational pull dominates over other forces, extends only about 930,000 miles into space, the distance where the Moon's orbit marks the boundary of our gravitational sphere of influence. 3I/ATLAS would pass roughly 180 times farther out than this gravitational boundary. Yet this same distance that guaranteed safety also provided unprecedented scientific opportunity. Modern telescopes can resolve details across such distances that would have been impossible just decades ago. The Hubble Space Telescope, with its ability to discern features as small as a few hundred meters across at 1.8 astronomical units, could potentially map surface characteristics of the interstellar visitor. The approach distance also placed 3I/ATLAS within range of multiple observational techniques. Radio telescopes could detect any electromagnetic emissions from the object. Infrared observatories could map its thermal characteristics as it warmed under solar heating. Optical telescopes could track its rotation and search for outgassing signatures that might reveal its composition. Perhaps most importantly, 1.8 astronomical units represented a distance that allowed extended observation campaigns. Unlike asteroid encounters that offer only brief glimpses during close approach, this separation would permit weeks of detailed study, both before and after the moment of closest proximity. Scientists would have time to coordinate observations, compare results, and build comprehensive understanding of their interstellar guest. The measurement also highlighted the remarkable precision of modern astrometry. Determining that 3I/ATLAS would approach to exactly 1.8 astronomical units required tracking the object's position to accuracies measured in arcseconds, angular measurements equivalent to spotting a dime from several miles away. This precision, accumulated over weeks of observations, provided confidence in predictions months into the future. The distance of 1.8 astronomical units would become the defining characteristic of the 3I/ATLAS encounter. Large enough to guarantee absolute safety, small enough to enable breakthrough science, close enough to capture public imagination, far enough to avoid panic or confusion. In the context of cosmic encounters, 1.8 astronomical units represented a perfect balance between accessibility and security. The universe had delivered an interstellar visitor with almost ideal geometry for human study, close enough to matter, far enough to ensure that our first detailed examination of a messenger from the stars would proceed with curiosity rather than fear. The approaching encounter with 3I/ATLAS revealed something remarkable about the geometry of cosmic discovery. Like Goldilocks finding the perfect porridge, astronomers realized they had been served an interstellar visitor positioned at exactly the right distance, not too close to be dangerous, not too far to be invisible, but precisely positioned for optimal scientific investigation. This Goldilocks zone of observation represented more than mere convenience. Astronomical history is filled with missed opportunities where important objects appeared either too close for comfort or too distant for detailed study. Comets that swing through the inner solar system often pass so near the Sun that they become impossible to observe during their most active periods. Distant objects in the outer solar system remain too faint for anything but basic characterization. 3I/ATLAS threaded this observational needle with almost suspicious precision. At 1.8 astronomical units, the visitor fell within the optimal range for every major telescope system on Earth and in space. Radio telescopes could detect potential emissions without interference from Earth's ionosphere. Optical telescopes could resolve surface features without atmospheric scattering overwhelming faint details. Infrared observatories could measure thermal characteristics without solar heating creating overwhelming background signals. The distance also provided what astronomers call light curve opportunities, the ability to observe how an object's brightness changes over time as it rotates and reveals different surface areas to Earth-based telescopes. These variations, measured over hours and days, reveal shape, rotation rate, and surface composition information that closer or more distant encounters often cannot provide. Perhaps most remarkably, the 1.8 astronomical unit approach would occur during a season when 3I/ATLAS appeared high in Earth's pre-dawn sky, positioned perfectly for extended observation sessions. Rather than requiring telescopes to peer through thick atmospheric layers near the horizon, the visitor would appear in the darkest part of the night sky, when atmospheric conditions typically provide the steadiest viewing. This geometric perfection raised intriguing questions about cosmic coincidences. The probability of an interstellar visitor arriving with such ideal positioning seemed vanishingly small. Random encounters with objects from other star systems should show no preference for Earth-friendly viewing geometry. Yet 3I/ATLAS appeared to have been specifically designed for human observation. The Goldilocks positioning also enabled something unprecedented in interstellar visitor studies: the possibility of coordinated observations across multiple wavelengths simultaneously. Previous encounters with objects like Oumuamua had provided only brief glimpses before the visitors disappeared beyond detection limits. 3I/ATLAS would remain observable for months, allowing comprehensive investigation across the entire electromagnetic spectrum. The distance proved ideal for another crucial reason. It permitted real-time observation of changes in the object's behavior. As 3I/ATLAS approached the Sun and began heating up, telescopes could monitor the development of any outgassing activity, tail formation, or surface changes. This evolutionary story, unfolding over weeks and months, would provide insights into how interstellar objects respond to stellar environments very different from their origins. The approach geometry also allowed for something rarely possible in astronomy: the luxury of multiple independent confirmations. With months of observation time available, different research groups could verify each other's measurements, ensuring that the scientific conclusions drawn from 3I/ATLAS would rest on solid observational foundations. International cooperation flourished within this Goldilocks zone. The extended timeline and optimal viewing conditions allowed observatories worldwide to coordinate their efforts, creating a global monitoring network that maximize scientific return from the encounter. Northern and southern hemisphere telescopes could provide continuous coverage as Earth rotated, ensuring that 3I/ATLAS remained under observation around the clock. The psychological impact of the perfect positioning cannot be understated. Unlike asteroid encounters that generate anxiety about potential impacts or distant object discoveries that remain abstract scientific curiosities, 3I/ATLAS offered the ideal balance of accessibility and safety that allowed pure scientific excitement to flourish. As summer turned toward fall in 2025, astronomers found themselves in the unprecedented position of having months to prepare for studying their first interstellar visitor under ideal conditions. The universe had provided what seemed like a carefully orchestrated natural experiment designed to reveal the secrets of objects that journey between the stars. But this perfect positioning also raised deeper questions about whether the encounter represented cosmic accident or something more intentional. Questions that would only intensify as observations revealed increasingly mysterious properties of the visitor from beyond our solar system. Speed takes on entirely different meaning when dealing with objects from interstellar space. 3I/ATLAS wasn't just moving fast by earthly standards, it was traveling at velocities that defied every expectation of how objects should behave in our cosmic neighborhood. To appreciate this speed, imagine watching a bullet in flight, then multiply that velocity by 170. That's 3I/ATLAS screaming through space at over 130,000 miles per hour. This velocity carried the unmistakable signature of an alien origin. Objects born in our solar system, shaped by millions of years of gravitational interactions with the Sun and planets, follow more sedate orbital patterns. Even the fastest comets from the outer reaches of our stellar neighborhood rarely exceed 40,000 miles per hour as they swing past Earth. 3I/ATLAS was moving more than 3 times faster, propelled by momentum acquired in an entirely different gravitational environment. The implications of this speed became clear when astronomers calculated how briefly the visitor would remain accessible for study. Unlike comets that spend months or years within range of Earth-based telescopes, 3I/ATLAS was executing a cosmic hit-and-run, racing through our solar system so quickly that observation opportunities would be measured in weeks rather than years. At these velocities, even the massive gravitational influence of our Sun could barely deflect the visitor's path. While solar system comets follow dramatic elliptical orbits that bring them close to the Sun before swinging back toward the outer darkness, 3I/ATLAS traced a hyperbolic arc that curved only slightly as it passed through our stellar neighborhood. The Sun's gravity might as well have been trying to lasso a speeding train. The speed also meant that every observation window was precious and irreplaceable. Telescopes tracking 3I/ATLAS had to adjust their pointing rates to follow an object moving across the sky faster than anything in their normal catalogue of targets. The technical challenges resembled trying to photograph a race car from the grandstands, possible, but requiring precision timing and careful preparation. Perhaps most remarkably, this extreme velocity hadn't diminished during the millions of years 3I/ATLAS had spent traveling between star systems. Unlike objects in Earth's atmosphere that slow down due to air resistance, or spacecraft that gradually lose speed to various drag forces, the visitor maintained its original momentum across interstellar distances where space provides no significant resistance to motion. The physics of such sustained high-speed travel paint a picture of cosmic loneliness. 3I/ATLAS had been racing through the galactic wilderness for eons, encountering virtually nothing that could alter its trajectory or velocity. The occasional gravitational influence of distant stars might have provided tiny course corrections over millions of years, but the fundamental speed remained unchanged, a fossil velocity from whatever catastrophic event had originally launched it into interstellar space. This preservation of velocity also meant that 3I/ATLAS carried kinetic energy measured in terms that dwarf human experience. Despite being only a few kilometers across, the visitor possessed momentum equivalent to thousands of nuclear weapons, not because of any exotic properties, but simply due to the relationship between mass and velocity that Einstein's equations describe. The racing timeline created a peculiar form of astronomical anxiety. Scientists knew they were witnessing a once-in-a-lifetime event, an opportunity to study interstellar material up close that might not repeat for decades or centuries. Yet the visitor's speed meant that every day of delay in observations represented irreplaceable data forever lost, as 3I/ATLAS receded toward undetectable distances. The velocity measurements also provided crucial clues about the visitor's origin. Computer models of galactic dynamics could work backward from the observed speed and trajectory to identify potential stellar nurseries where 3I/ATLAS might have formed. The mathematical fingerprints suggested origins in populations of stars billions of years older than our Sun, ancient stellar neighborhoods that existed when our galaxy was younger and more chaotic. As September 2025 approached and 3I/ATLAS raced toward its closest approach to the Sun, the speed that made this visitor so remarkable also imposed a cruel deadline on human curiosity. We had months, not years, to unlock the secrets of this messenger from the stars. Every observation session was measured against the relentless countdown of cosmic velocity, racing to understand a visitor that would never slow down, never return, and never again provide such an opportunity for detailed study. The universe had delivered a priceless scientific specimen, but wrapped it in a package of pure speed that transformed discovery into a race against time itself. Time takes on special urgency when your research subject is racing through the solar system at impossible speeds. As August 2025 progressed, astronomers worldwide found themselves working against a countdown clock that operated according to the merciless precision of orbital mechanics. Every day that passed brought 3I/ATLAS closer to its date with solar conjunction, the period when it would disappear behind the sun's glare and become temporarily invisible to Earth-based telescopes. The observation timeline broke into distinct phases, each offering different scientific opportunities and challenges. The approach phase, running from discovery through early October, provided steadily improving viewing conditions as 3I/ATLAS brightened and revealed more details to waiting telescopes. During this period, the visitor would transform from a faint point of light into a resolvable object, whose surface features and activity patterns could be studied in unprecedented detail. But the clock was ticking toward October 29th, 2025, perihelion, when 3I/ATLAS would reach its closest point to the Sun. This moment represented both the climax of the visitor's solar system passage and the beginning of a frustrating blackout period that would hide the most dramatic phase of the encounter from human eyes. Solar conjunction occurs when an object's orbital path carries it directly behind the Sun as viewed from Earth. For 3I/ATLAS, this cosmic hide-and-seek would begin in late September and continue through early December, creating a 2-month gap in observations just when the visitor should be most active. Solar heating would drive maximum outgassing rates, potentially creating spectacular tail displays and revealing internal composition, all invisible to telescopes blinded by our star's overwhelming glare. The cruel irony wasn't lost on the astronomical community. After waiting years for another interstellar visitor to study, the universe had provided one with nearly perfect approach geometry, only to hide its most interesting behavior behind the brightest object in our solar system. It was as if cosmic forces were deliberately teasing human curiosity. This approaching blackout created a sense of urgency that transformed the normally methodical pace of astronomical research into something resembling emergency response. Telescope scheduling committees, which typically plan observations months in advance, began granting emergency allocations of observing time. Research proposals that normally required peer review and competitive evaluation were fast-tracked through approval processes. International cooperation accelerated to match the compressed timeline. The European Space Agency coordinated with NASA to ensure continuous coverage as Earth's rotation carried different telescopes into optimal viewing positions. Amateur astronomy networks mobilized thousands of smaller telescopes to contribute photometric measurements that professional observatories couldn't provide around the clock. The countdown also drove innovation in observational techniques. Knowing that post-conjunction observations would deal with a much fainter, more distant target, engineers worked to optimize telescope sensitivity and develop new data processing methods that could extract maximum information from minimal signal. Software systems were updated to handle the rapid position changes of the fast-moving visitor. Perhaps most remarkably, the time pressure inspired audacious proposals for space-based observations that could continue during Earth's blackout period. Mission planners investigated whether existing spacecraft could be redirected to observe 3I/ATLAS from different vantage points. The Mars Reconnaissance Orbiter, positioned perfectly to view the visitor during its October close approach, received new instructions to attempt imaging during Earth's blindness. The psychological impact of the countdown affected public interest as well. Unlike typical astronomical events that unfold over predictable timeframes, the 3I/ATLAS encounter carried genuine suspense about what might be discovered before the observation window closed. Social media filled with daily updates, amateur photographs, and speculation about what the December reappearance might reveal. Educational institutions adapted their curricula to match the unfolding timeline. Students worldwide followed the approaching conjunction as a real-time lesson in orbital mechanics and observational astronomy. The countdown became a shared global experience, with millions of people checking daily updates on the visitor's approach towards solar invisibility. As September progressed and the available observation time dwindled, scientists faced difficult choices about which measurements to prioritize before the blackout. Limited telescope time had to be allocated between imaging campaigns, spectroscopic analysis, and photometric monitoring. Each observation session was planned with the knowledge that opportunities lost to weather, equipment failures, or scheduling conflicts might never return. The countdown wasn't just measuring time until solar conjunction. It was measuring the remaining opportunities to solve the mystery of 3I/ATLAS before the visitor disappeared into the sun's glare, carrying its secrets into a 2-month period of cosmic silence. The comfortable distance of 1.8 astronomical units eliminated every concern about 3I/ATLAS posing a physical threat to Earth, but it created entirely new categories of cosmic mystery. Safety, it turned out, was just the beginning of the story. As telescopes began their detailed examination of the interstellar visitor, they discovered that being physically harmless didn't mean being astronomically quiet. The first hint of 3I/ATLAS's unusual nature came through spectroscopic analysis, the technique of splitting starlight into its component colors to reveal chemical composition. When the James Webb Space Telescope turned its infrared sensors toward the visitor in early August, the results defied every expectation built from studying previous interstellar objects. Instead of the water-dominated chemistry typical of solar system comets, 3I/ATLAS showed an overwhelming abundance of carbon dioxide. This chemical signature was more than just unusual. It was almost impossible according to conventional models of how comets should behave. The carbon dioxide to water ratio exceeded 8:1, placing 3I/ATLAS in a category entirely its own. Most solar system comets show the opposite pattern, with water dominating their volatile inventory by factors of 10 to 100. Here was a visitor that seemed to be made of the wrong materials entirely. The safe distance that guaranteed Earth's protection also enabled the kind of prolonged, detailed study that closer encounters often preclude. Without concerns about impact hazards or gravitational disruption, telescopes could be programmed for systematic observation campaigns that built comprehensive understanding over weeks and months rather than hours or days. But the more astronomers studied 3I/ATLAS, the more questions emerged. The visitors' unusual chemistry was accompanied by behavioral patterns that challenged theoretical understanding. The carbon dioxide emissions weren't confined to a small region around the nucleus, as outgassing models predicted, but extended across distances larger than Earth's orbit around the Sun. Somehow, a nucleus only a few kilometers across was generating and maintaining a gas cloud with dimensions that dwarfed entire planetary systems. The morphology of this extended emission region suggested processes operating on scales that conventional comet physics struggled to explain. Rather than the compact, roughly spherical coma typical of solar system comets, 3I/ATLAS displayed an asymmetric structure that seemed to respond to solar heating in unexpected ways. The gas cloud's shape and extent changed over time, but not according to the patterns that sublimating ice models predicted. Radio observations added another layer of mystery. While most comets remain electromagnetically silent, except for the faint emissions associated with gas discharge, 3I/ATLAS occasionally displayed radio signatures that hinted at more complex electromagnetic interactions. These signals were subtle and intermittent, but their presence suggested that the visitors' interaction with the solar environment involved physics beyond simple thermal heating of ice. The safety of the encounter paradoxically enabled scientists to consider explanations that might have been dismissed as too exotic if the visitor had posed any threat. Without the need to focus on impact prediction or gravitational modeling for planetary defense, research attention could turn to the more interesting question of what 3I/ATLAS actually was and how it had acquired such unusual properties. The extended observation timeline allowed for something rarely possible in astronomy: real-time monitoring of changes in the visitor's behavior. As 3I/ATLAS approached the Sun and experienced increasing thermal stress, telescopes could track the evolution of its gas production, the development of tail structures, and potential fragmentation events. This dynamic story unfolded over months, providing insights into how interstellar objects respond to environmental conditions very different from their origins. Perhaps most intriguingly, the safe distance enabled detailed astrometric measurements, precise tracking of the visitor's position over time, that could reveal whether 3I/ATLAS was following purely gravitational motion or experiencing additional forces. These measurements required months of patient observation to accumulate the precision needed to detect subtle trajectory deviations. The combination of safety and mystery transformed 3I/ATLAS from a potential threat into the most intensively studied small object in astronomical history. The visitor's secure trajectory allowed pure scientific curiosity to flourish without the distraction of existential concerns. But the mysteries uncovered through this prolonged study suggested that 3I/ATLAS might be far stranger than its safe approach initially implied. Being protected from a cosmic visitor, it seemed, was no guarantee of being protected from cosmic revelation. While Earth prepared for its safe but spectacular encounter with 3I/ATLAS, another perspective on the interstellar visitor was developing 140 million miles away on the surface of Mars. The red planet's position during the visitor's approach offered a unique vantage point that would prove crucial for understanding the three-dimensional structure of this cosmic mystery. Mars sits in a fundamentally different orbital relationship to 3I/ATLAS than Earth does. While our planet would experience the visitor's closest approach at a comfortable 1.8 astronomical units, Mars faced a much more dramatic encounter. On October 3, 2025, 3I/ATLAS would sweep past the red planet at just 0.2 astronomical units, roughly 18 million miles, close enough that Martian observers would see details invisible from Earth's more distant vantage point. This geometric difference offered unprecedented scientific opportunities. The same object viewed from two widely separated locations provides what astronomers call parallax observations, measurements that reveal three-dimensional structure and motion patterns impossible to detect from a single viewpoint. Like closing one eye and then the other to gauge depth perception, Earth and Mars would provide complementary perspectives on 3I/ATLAS's true nature. The Mars Reconnaissance Orbiter, circling the red planet since 2006, carried instruments originally designed for geological survey work that proved remarkably suited for interstellar visitor observation. The spacecraft's high-rise camera, capable of resolving features as small as a dining table from orbit, would potentially capture the highest resolution images ever obtained of an interstellar object. More importantly, Mars would maintain visual contact with 3I/ATLAS throughout the crucial period when Earth lost sight of the visitor behind solar conjunction. While terrestrial telescopes struggled with the sun's overwhelming glare, Martian observers would have unobstructed views of the visitor's most active phase. The red planet would serve as humanity's remote outpost, maintaining surveillance when home-based observations became impossible. The viewing geometry from Mars revealed aspects of 3I/ATLAS that Earth-based observers could barely glimpse. The visitor's extended carbon dioxide coma, which appeared as a subtle elongation in terrestrial telescopes, showed dramatic asymmetry when observed from Mars's perspective. The gas cloud structure suggested complex internal dynamics that single viewpoint observations had missed entirely. Thermal infrared observations from Mars provided another unique advantage. The red planet's thinner atmosphere creates less interference for infrared astronomy than Earth's water vapor-rich environment. Martian observations of 3I/ATLAS's heat signature revealed temperature patterns that suggested non-uniform heating or possible internal energy sources beyond simple solar illumination. The temporal advantages of Martian observation proved equally valuable. While Earth experienced a 2-month blackout period during solar conjunction, Mars maintained continuous monitoring capability throughout the visitor's perihelion passage. This uninterrupted coverage captured the full evolutionary story of how 3I/ATLAS responded to maximum solar heating, data that would have been permanently lost without the Martian perspective. Radio observations from Mars faced unique challenges but offered corresponding rewards. The red planet's lack of a substantial ionosphere eliminated many sources of radio interference that plagued Earth-based observations. The trade-off came in reduced sensitivity due to smaller antenna systems, but the cleaner signal environment more than compensated for the equipment limitations. The coordination between Earth and Mars observations required unprecedented precision in spacecraft operations. Commands sent to the Mars Reconnaissance Orbiter had to account for the 8 to 20-minute communication delay between planets, depending on their relative positions. Observation schedules were planned months in advance, with backup procedures in case communication windows closed unexpectedly. The Martian observations also provided crucial calibration data for Earth-based measurements. By observing the same features from different angles and distances, astronomers could validate their models of 3I/ATLAS's size, shape, and activity patterns. Discrepancies between Earth and Mars observations highlighted measurement uncertainties and guided refinements in analysis techniques. Perhaps most remarkably, the Martian perspective revealed the true scale of 3I/ATLAS's gas production. What appeared as a modest coma from Earth's distant viewpoint showed itself as an enormous cloud of material when viewed from Mars's closer position. The extended emission region stretched across angular dimensions that dwarfed the planet's apparent size, suggesting gas production rates that challenged theoretical understanding. As October 2025 approached and Earth prepared to lose sight of 3I/ATLAS behind the sun's glare, Mars stood ready to continue the vigil. The red planet had become humanity's forward observation post, positioned to witness the climactic moments of the interstellar encounter, when thermal stress peaked and the visitor's true nature might finally be revealed. The view from Mars would prove that perspective matters enormously when studying cosmic phenomena. and that sometimes the best seat in the house isn't the closest one to home. October 29th, 2025 marked the most frustrating date in modern astronomy. The moment when 3I/ATLAS reached perihelion, its closest approach to the Sun, while remaining completely invisible to every telescope on Earth. Solar conjunction had created a cosmic curtain that hid the visitor's most dramatic performance from human eyes, just when thermal stress should have driven its activity to spectacular heights. Behind the Sun's blinding glare, 3I/ATLAS was experiencing temperatures and radiation levels unlike anything it had encountered during millions of years of interstellar wandering. Solar energy was heating its nucleus to temperatures that could vaporize ice, crack rock, and drive explosive outgassing that might fragment the entire object into a cloud of debris. The physics of what was happening remained largely theoretical, constructed from models and indirect evidence rather than direct observation. Computer simulations suggested that the visitor's unusual carbon dioxide composition would respond to solar heating in ways very different from typical comets. Instead of the gradual sublimation that characterizes water ice, carbon dioxide could undergo rapid phase transitions that create internal pressure and potentially explosive expansion. The extended carbon dioxide coma that had puzzled astronomers throughout the approach phase might have been just a preview of October's hidden fireworks. Maximum solar heating could drive gas production rates that dwarfed anything observed during the visible portion of the encounter. If theoretical models were correct, 3I/ATLAS might be generating a tail structure so spectacular that it would rival the great comets of history, all invisible behind the Sun's overwhelming brightness. Thermal stress analysis suggested other possibilities that would remain hidden until the December reappearance. The temperature gradients between the sunlit and shadowed portions of the nucleus could create mechanical forces sufficient to fracture the object entirely. Some interstellar visitors are thought to be loose aggregates of material held together by weak gravitational and cohesive forces. Such structures might not survive the thermal shock of close solar approach. The timing of perihelion passage also coincided with the peak period for potential electromagnetic interactions. The solar wind, charged particles streaming from the Sun at millions of miles per hour, would be interacting with 3I/ATLAS at maximum intensity. If the visitor possessed unusual electrical properties or magnetic characteristics, these interactions might generate radio emissions, plasma effects, or other phenomena that would normally be prime targets for Earth-based observation. Mars Reconnaissance Orbiter provided the only window into October's hidden drama, though even this remote outpost faced significant challenges during the critical period. The spacecraft's instruments were designed for planetary geology rather than comet observation, and the extreme solar heating that might be affecting 3I/ATLAS also complicated thermal infrared measurements from the orbiting observatory. The few observations that Mars could provide painted a picture of dramatically evolving activity. Images captured during early October showed the visitor's coma expanding and developing asymmetric structures that suggested jet-like emissions from specific regions on the nucleus. The gas production rates appeared to be increasing exponentially as 3I/ATLAS approached perihelion, confirming theoretical predictions about carbon dioxide sublimation under intense solar heating. Perhaps most tantalizing, radio monitoring from Mars detected intermittent signals that coincided with the visitor's closest solar approach. These emissions were unlike anything in the catalogue of natural radio sources, displaying modulation patterns and frequency characteristics that resembled artificial transmissions. The signals were too weak and brief for detailed analysis, but their timing suggested a connection to the extreme environmental conditions during perihelion passage. The hidden drama of October represented more than missed observational opportunities. It symbolized the fundamental challenge of studying cosmic phenomena that operate on schedules indifferent to human convenience. The universe's most interesting events often occur in places, or at times, that make observation difficult or impossible from Earth's perspective. The theoretical implications of the unseen perihelion passage would drive scientific speculation throughout the remaining months of 2025. Computer models could predict what might have happened during solar conjunction, but only the December reappearance would reveal whether 3I/ATLAS had survived its close encounter with our star unchanged, transformed, or fragmented beyond recognition. The hidden drama also highlighted the importance of multiple observation platforms for studying transient cosmic events. Future interstellar visitor encounters would benefit from spacecraft positioned at strategic locations throughout the solar system, ensuring that crucial evolutionary phases wouldn't be lost to observational geometry. As October ended and November began, telescopes worldwide prepared for 3I/ATLAS to emerge from behind the sun's glare. The visitor's reappearance would either confirm theoretical models about interstellar object behavior under extreme thermal stress, or reveal surprises that would force fundamental revision of those models. The drama hidden behind the sun was about to be revealed, and the astronomical community held its collective breath to see what October's unseen performance had done to their mysterious visitor from the stars. December 2025 would mark one of the most anticipated moments in modern astronomy. The reappearance of 3I/ATLAS from behind the sun's glare after 2 months of cosmic invisibility. As the visitor emerged from solar conjunction, telescopes worldwide stood ready to capture humanity's final detailed look at this messenger from interstellar space before it raced back into the galactic wilderness forever. The reappearance geometry offered both opportunities and challenges that would define the success of this ultimate observation campaign. 3I/ATLAS would first become visible in the pre-dawn sky, rising before the sun in the constellation Virgo. This positioning provided ideal viewing conditions for extended observation sessions, when atmospheric turbulence typically reaches minimum levels and telescopes can achieve their finest resolution. But the visitor would be racing away from the sun at over 150,000 miles per hour, growing fainter each night as distance reduced the amount of reflected sunlight reaching Earth-based detectors. What had been a challenging but manageable target during the approach phase would become an exercise in pushing astronomical instrumentation to its absolute limits. The first priority for December observations was damage assessment, determining whether 3I/ATLAS had survived its close solar encounter intact or had fragmented under thermal stress. Previous comets have been observed to split apart during perihelion passage, sometimes creating spectacular displays of multiple components diverging along slightly different trajectories. If 3I/ATLAS had undergone similar fragmentation, the December reappearance might reveal a string of objects rather than a single visitor. Spectroscopic analysis would provide the crucial test of theoretical models about how the visitor's unusual carbon dioxide composition responded to extreme solar heating. If the models were correct, the post-perihelion chemistry should show dramatic changes, either complete depletion of volatile materials or the emergence of new spectral features created by thermal processing of the nucleus. The morphology of any coma or tail structures would tell the story of what happened during the hidden October drama. Computer simulations predicted that maximum solar heating should have driven gas production rates far beyond anything observed during the approach phase. The December reappearance would reveal whether these predictions matched reality, or whether 3I/ATLAS followed different physics than theoretical understanding suggested. International coordination reached unprecedented levels as the December observation window approached. The brief timeline and challenging observing conditions required every available telescope to contribute to the campaign. Northern and Southern Hemisphere observatories coordinated schedules to provide continuous coverage as Earth's rotation carried different facilities into optimal viewing positions. The James Webb Space Telescope received priority allocation for infrared spectroscopy that could detect trace compounds invisible to ground-based instruments. The Hubble Space Telescope prepared for high-resolution imaging that might reveal surface features or fragmentation signatures. Radio telescope networks worldwide stood ready to monitor for any electromagnetic emissions that might have been triggered by the perihelion passage. Amateur astronomy communities mobilized thousands of smaller telescopes to contribute photometric measurements that professional observatories couldn't provide around the clock. The distributed network of citizen scientists had become crucial for maintaining continuous monitoring of rapidly changing targets like 3I/ATLAS. The technical challenges of December observations pushed instrument capabilities toward their limits. Adaptive optics systems that corrected for atmospheric turbulence required constant adjustment to track the visitor's rapid motion across the sky. Spectrographs designed for stationary targets needed special calibration procedures to handle objects moving at significant fractions of arcsecond per minute. The observation campaign also faced weather-dependent uncertainties that could eliminate crucial data collection opportunities. December weather patterns in both hemispheres often create extended periods of cloud cover that can shut down optical astronomy for days at a time. Backup observation strategies were developed for multiple contingencies, including alternative telescopes and rapid response protocols for brief clear weather windows. Perhaps most importantly, the December observations represented humanity's final opportunity to gather data about 3I/ATLAS before the visitor disappeared beyond the detection limits of even our most powerful telescopes. Unlike periodic comets that return for multiple observation opportunities, interstellar visitors offer only one chance for detailed study during their brief passage through our cosmic neighborhood. The scientific questions that would be answered or deepened during December's revelation window would influence theoretical understanding of interstellar objects for generations. Had 3I/ATLAS survived its solar encounter? What had the extreme heating revealed about its internal structure and composition? Did the visitor's behavior match theoretical predictions? Or would the reappearance force fundamental revision of how astronomers understand these cosmic wanderers? As December began and the first tentative detections of 3I/ATLAS emerged from the sun's glare, the astronomical community prepared for revelations that would either solve the mystery of this interstellar visitor or transform it into an even deeper puzzle that would haunt cosmic science long after the visitor itself had vanished into interstellar space. Tracking 3I/ATLAS presented astronomical observatories with their greatest technical challenge since the space age began, photographing and analyzing an object moving so fast across the sky that conventional observation techniques simply couldn't keep pace. The visitor's interstellar velocity translated into angular motion that pushed telescope tracking systems far beyond their normal operational parameters. Most celestial objects move so slowly across Earth's sky that their motion is essentially imperceptible during a single night's observation. Stars remain virtually fixed in position. Planets drift at rates measured in arc-minutes per day, and even fast-moving asteroids typically require hours to show detectable position changes. 3I/ATLAS, by contrast, was racing across the stellar background at rates that created a new category of observational challenge. The fundamental problem lay in the relationship between linear speed and angular velocity. While 3I/ATLAS maintained a constant velocity of roughly 130,000 miles per hour through space, its apparent motion across Earth's sky varied dramatically with distance. During closest approach, the visitor would sweep across angular distances equivalent to the moon's diameter in just a few hours, motion fast enough to blur images taken with exposure times longer than a few minutes. Professional observatories had to fundamentally modify their operation procedures to handle such rapid target motion. Telescope pointing systems designed for tracking the slow drift of celestial objects required software updates and hardware modifications to follow 3I/ATLAS without losing target lock. The precision demands were extraordinary, maintaining focus on an object smaller than a city while it raced across the sky faster than military aircraft. Hubble Space Telescope faced particularly acute challenges because its pointing system was optimized for the ultra-precise stability needed to resolve distant galaxies and faint nebulae. Tracking 3I/ATLAS required the observatory to operate in a mode that compromised some of this stability in favor of rapid target acquisition and following capability. Even with these modifications, observation windows were limited to periods when the target motion fell within acceptable tracking rates. Ground-based telescopes dealt with additional complications from atmospheric refraction and turbulence. As 3I/ATLAS moved across different portions of the sky, its apparent position shifted not only due to actual motion, but also due to changing atmospheric conditions. Adaptive optic systems that normally corrected for steady-state atmospheric effects had to be recalibrated continuously to handle a target whose position changed faster than the correction algorithms could respond. The speed of 3I/ATLAS also created unprecedented demands on data processing systems. Traditional astronomical imaging involves taking multiple exposures of the same field over extended periods, then combining the results to improve signal-to-noise ratios. With 3I/ATLAS, each image captured the visitor at a slightly different position, requiring new software techniques to align and stack observations while accounting for the target's rapid motion. Spectroscopic analysis faced even greater challenges. Obtaining detailed spectra requires concentrating light from the target object into extremely narrow slits or fiber optic feeds for several minutes or hours. With 3I/ATLAS moving so rapidly, keeping the visitor's light properly aligned with spectrograph inputs demanded real-time adjustment capabilities that pushed instrument design to its limits. Radio telescope observations encountered their own unique difficulties. Unlike optical telescopes that can quickly repoint to track moving targets, radio dishes often require several minutes to slew between positions due to their enormous mass and size. The largest radio telescopes simply couldn't track 3I/ATLAS continuously, instead relying on brief snapshot observations as the visitor passed through their fields of view. The rapid motion also compressed normal observation timelines in ways that fundamentally changed how astronomical research could be conducted. Where typical targets allow weeks or months for careful observation planning and data collection, 3I/ATLAS demanded real-time decision-making about observation priorities. Scientists had to choose between different types of measurements, knowing that opportunities lost to weather, equipment problems, or scheduling conflicts would never return. International coordination became essential because no single observatory could maintain continuous coverage of such a fast-moving target. As Earth's rotation carried one telescope out of optimal viewing position, another facility on a different continent had to seamlessly take over observations. This global relay race required unprecedented cooperation between observatories that normally operated independently. Amateur astronomers faced the greatest technical challenges of all. While professional observatories could modify software and hardware to handle extreme target motion, backyard telescopes typically lacked the sophisticated tracking systems needed to follow 3I/ATLAS accurately. Many amateur observations relied on brief exposures and careful timing rather than the long exposure techniques that normally reveal faint cosmic details. The speed of 3I/ATLAS ultimately transformed astronomical observation from a patient, methodical process into something resembling emergency response. Every clear night represented a precious opportunity to gather data about a target that was literally racing away from Earth's ability to study it. The visitor's velocity had turned astronomy into a sport where success was measured not just by the quality of observations, but by the speed at which they could be obtained and analyzed. This technological challenge would influence future interstellar visitor observations, driving development of new tracking systems, faster data processing capabilities, and more flexible observation scheduling protocols designed to handle the unique demands of studying cosmic objects that refuse to slow down for human convenience. When scientists first pointed their most sensitive instruments toward 3I/ATLAS and analyzed the chemical fingerprints in its reflected sunlight, they discovered something that challenged every assumption about what interstellar visitors should look like. The composition, revealed through spectroscopic analysis, was so unusual that it forced astronomers to question whether their understanding of comet chemistry was fundamentally incomplete. The shock came from the carbon dioxide measurements, where typical comets show modest amounts of CO2 mixed with abundant water ice. 3I/ATLAS displayed the opposite pattern. The carbon dioxide to water ratio exceeded 8:1, a proportion so extreme that it placed the visitor in a category entirely its own. To appreciate how unusual this chemistry was, imagine expecting to find a typical Earth rock and instead discovering something made primarily of diamond. The basic materials were familiar, but the proportions defied explanation. This chemical signature became even more mysterious when astronomers considered how such compositions could form naturally. In the cold depths of space where comets typically condense from primordial gas and dust, water ice should dominate the volatile inventory by enormous margins. Carbon dioxide, while present, usually appears as a minor component that sublimates away quickly when heated by starlight. The James Webb Space Telescope's detailed infrared spectroscopy revealed additional surprises that deepened the mystery. Not only was 3I/ATLAS rich in carbon dioxide, but the CO2 emissions extended across distances larger than entire planetary orbits. Somehow, a nucleus only a few kilometers across was generating and maintaining a gas cloud with dimensions that dwarfed Earth's path around the Sun. The scale of this emission region challenged fundamental understanding of how outgassing works. Traditional comet models predict that gas production occurs in a relatively narrow zone around the nucleus where solar heating drives sublimation of surface ices. The extended carbon dioxide cloud surrounding 3I/ATLAS suggested either extraordinarily vigorous activity from a very small source, or mechanisms that distributed gas-producing material across much larger volumes than conventional physics allowed. SphereX mission data added another layer of complexity to the chemical mystery. Wide-field infrared mapping revealed that the carbon dioxide wasn't distributed uniformly throughout the extended coma, but showed complex structures and variations that changed over time scales of hours to days. The patterns suggested active jets or directed emissions rather than the symmetric expansion typical of simple sublimation processes. The contrast with previous interstellar visitors made 3I/ATLAS even more puzzling. Oumuamua had shown no detectable outgassing whatsoever, appearing more like a bare rock than a typical ice-rich comet. 2I/Borisov had displayed elevated carbon monoxide rather than carbon dioxide, suggesting formation in extremely cold environments. Now 3I/ATLAS presented a third, completely different chemical signature, implying that interstellar space harbored far more diversity than theoretical models predicted. The absence of expected water signatures created additional complications for standard interpretation. Early observations by the Swift Observatory had detected hydroxyl radicals, typically reliable indicators of water vapor being broken apart by solar ultraviolet radiation. Yet subsequent high-sensitivity searches for water emission lines came up nearly empty, suggesting that either the water was there but hidden, or the hydroxyl detections had been misinterpreted. The temperature requirements for 3I/ATLAS's observed chemistry didn't match any known formation environment in our solar system. Carbon dioxide dominance typically requires intermediate temperatures, where water exists as vapor, but CO2 can still condense from the gas phase. Such conditions might exist in the asteroid belt region around some stars, but creating objects with such extreme compositional ratios would require very specific and probably rare circumstances. Laboratory studies of carbon dioxide ice behavior under space-like conditions provided some clues about how the unusual chemistry might produce the observed phenomena. CO2. Ice sublimes much more readily than water ice at the same temperature, potentially explaining why the visitor showed such vigorous activity at distances where water-rich comets remain relatively quiet. But the laboratory analogues couldn't fully explain the enormous scale of the carbon dioxide emission region. Even assuming extremely efficient gas production from the nuclear surface, basic physics limited how far sublimated material could travel before being dispersed by solar wind pressure and thermal expansion. The observed dimensions suggested either internal energy sources beyond solar heating or gas production mechanisms that conventional models couldn't account for. The chemical mystery of 3I/ATLAS extended beyond simple curiosity about unusual compositions. If interstellar visitors routinely displayed such exotic chemistry, it implied that planetary formation processes around other stars produced materials very different from anything in our local cosmic environment. The diversity already apparent in just 3 confirmed interstellar objects suggested a galaxy filled with chemical surprises. As December observations began revealing how the visitor's chemistry had evolved during its hidden passage through perihelion, scientists prepared for potential revelations that would either solve the compositional puzzle or transform it into an even deeper mystery about the true nature of materials that journey between the stars. The 1.8 astronomical unit approach distance of 3I/ATLAS created a cosmic laboratory with nearly perfect conditions for studying an interstellar visitor in unprecedented detail. This carefully calibrated separation, close enough for detailed analysis, distant enough for safety and extended observation, enabled discoveries that would have been impossible at any other range. At closer distances, 3I/ATLAS would have presented overwhelming technical challenges. Solar heating effects would have been more extreme, potentially driving outgassing rates that obscured the nucleus beneath clouds of gas and dust. The visitor's apparent motion across the sky would have been too rapid for many observation techniques, particularly the extended exposure times needed for high-resolution spectroscopy. Most critically, closer approaches would have compressed the observation timeline into days rather than months, eliminating opportunities for the comprehensive studies that revealed the visitor's most intriguing properties. More distant encounters would have rendered 3I/ATLAS essentially invisible to detailed investigation. The inverse square law governing reflected sunlight meant that doubling the distance would have reduced the visitor's apparent brightness by a factor of 4. At distances typical of outer solar system objects, even the most sensitive telescopes would have struggled to detect anything beyond basic positional measurements and crude estimates of overall brightness. The 1.8 astronomical unit separation placed 3I/ATLAS in the optimal zone for spectroscopic analysis, the technique that revealed its extraordinary chemical composition. Spectroscopy requires collecting enough photons from the target to split them into their component wavelengths and identify the absorption or emission lines that reveal chemical composition. Too close, and the target becomes so bright that detectors saturate before useful exposure times are reached. Too far, and insufficient light reaches the instruments to enable meaningful analysis. This Goldilocks distance also enabled what astronomers call light curve analysis, monitoring how an object's brightness changes over time as different surface areas rotate into and out of view. These subtle brightness variations, measured over hours and days, reveal information about size, shape, rotation rate, and surface composition that cannot be obtained through any other technique. The extended observation timeline possible at 1.8 astronomical units allowed for months of light curve monitoring that built a comprehensive understanding of the visitor's physical properties. The distance proved ideal for another crucial measurement technique, astrometry, the precise tracking of position over time. Detecting whether 3I/ATLAS experienced non-gravitational forces, subtle pushes from outgassing that could alter its trajectory, required months of patient position measurements accurate to tiny fractions of arcseconds. Closer approaches would have made such precise tracking impossible due to the visitor's rapid motion. More distant encounters would have reduced positional accuracy below the threshold needed to detect small trajectory deviations. radio astronomy benefited enormously from the optimal distance. Radio telescopes searching for electromagnetic emissions from 3I/ATLAS needed the visitor to be close enough that any signals remained detectable above the background noise of space, but far enough that Earth's own radio interference didn't overwhelm faint cosmic transmissions. The 1.8 astronomical unit separation provided this perfect balance, enabling months of sensitive radio monitoring that revealed subtle electromagnetic signatures invisible at other distances. The approach distance also created ideal conditions for polarimetry, analyzing how reflected sunlight becomes polarized by interaction with dust particles in the visitor's coma. This technique reveals information about particle size distributions and composition that supplements direct spectroscopic measurements. The polarization effects are subtle and require extended observation periods to detect reliably, something only possible during the months-long observation window that 1.8 astronomical units provided. Perhaps most remarkably, the distance enabled simultaneous multi-wavelength observations that created a comprehensive portrait of 3I/ATLAS across the entire electromagnetic spectrum. Optical telescopes could monitor visible light reflected from the surface. Infrared instruments could detect thermal emission that revealed temperature patterns and composition. Radio telescopes could search for electromagnetic activity. Ultraviolet observations could study how solar radiation interacted with gas in the visitor's coma. The coordination of these diverse observation techniques required the extended timeline that only the 1.8 astronomical unit approach distance could provide. Rapid flybys compress observation opportunities into brief windows where choices must be made between different types of measurements. The months-long accessibility of 3I/ATLAS eliminated such compromises, allowing comprehensive investigation across multiple wavelengths simultaneously. The optimal distance also enabled something unprecedented in interstellar visitor studies: the luxury of repeat observations to verify unexpected results. When initial measurements revealed 3I/ATLAS's unusual chemistry, astronomers had time to conduct follow-up observations that confirmed the findings and explored their implications. This capability for verification and refinement transformed single snapshot measurements into robust scientific understanding. As December observations revealed how the visitor had evolved during its hidden perihelion passage, the value of the 1.8 astronomical unit approach distance became even more apparent. The discoveries enabled by this optimal separation would influence theoretical understanding of interstellar objects for generations, demonstrating that cosmic encounters succeed not just through proximity, but through finding the perfect balance between accessibility and careful study. The approach of 3I/ATLAS triggered the most coordinated international astronomical observation campaign in history, transforming competition between research institutions into unprecedented cooperation focused on extracting maximum scientific value from humanity's brief encounter with an interstellar visitor. This global mobilization represented astronomy at its finest. Nations and organizations setting aside territorial interests to pursue shared scientific goals. The coordination began within hours of the visitor's discovery, as automated alert systems notified observatories worldwide about the detection of another interstellar object. Unlike typical astronomical discoveries that generate polite interest and eventual follow-up observations, 3I/ATLAS demanded immediate action from every facility capable of contributing meaningful data. The compressed timeline and unique scientific opportunity eliminated normal institutional barriers to cooperation. NASA's Jet Propulsion Laboratory served as the central coordination hub, maintaining real-time databases of observation schedules, target coordinates, and preliminary results that could be accessed by research groups worldwide. This transparency enabled efficient allocation of telescope time and prevented duplication of effort during the critical observation windows, when every clear night represented irreplaceable scientific opportunity. The European Space Agency contributed sophisticated tracking capabilities through its deep space network, providing precise positional measurements that refined trajectory calculations and enabled accurate pointing for other observatories. The collaboration extended beyond simple data sharing to include joint observation planning and coordinated instrument configurations that maximize the complementary value of different telescope systems. Ground-based observatories in both hemispheres created a continuous monitoring network that followed 3I/ATLAS around the clock, as Earth's rotation carried different facilities into optimal viewing positions. The Gemini telescopes in Hawaii and Chile provided high-resolution imaging across the day-night boundary. The Very Large Telescope Array in Chile contributed spectroscopic capabilities when Northern Hemisphere instruments faced daylight constraints. Amateur astronomy networks mobilized with remarkable speed and efficiency, contributing thousands of smaller telescopes to photometric monitoring campaigns that professional observatories couldn't provide continuously. The distributed network of citizen scientists became crucial for maintaining 24-hour coverage of brightness variations that could reveal rotation rates, surface features, and activity patterns invisible to intermittent professional observations. Radio telescope arrays worldwide coordinated their efforts to provide comprehensive electromagnetic monitoring across multiple frequency bands. The Very Large Array in New Mexico, FAST in China, and radio telescopes across Europe synchronized their observation schedules to ensure continuous coverage of potential radio emissions from 3I/ATLAS throughout its passage past Earth. Space-based observatories required the most complex coordination due to their limited availability and competing scientific priorities. The Hubble Space Telescope and James Webb Space Telescope received emergency time allocations that disrupted carefully planned observation schedules for other projects. The Swift Observatory and other orbital platforms contributed ultraviolet and X-ray monitoring that would have been impossible from ground-based facilities. The international cooperation extended to data processing and analysis pipelines that could handle the unprecedented volume of observations streaming from dozens of facilities simultaneously. Standardized data formats and real-time sharing protocols enabled researchers worldwide to access and analyze observations within hours of collection, accelerating the pace of scientific discovery to match the compressed timeline of the visitor's approach. Cultural and language barriers dissolved in the face of shared scientific excitement about 3I/ATLAS. Research groups that normally published results months or years after observations began releasing preliminary findings within days, creating a collaborative atmosphere where discoveries built upon each other in real time, rather than through the traditional slow process of peer review and publication. The coordination faced significant technical challenges from the visitors' rapid motion across the sky. Different observatories needed constantly updated pointing coordinates as 3I/ATLAS raced through the stellar background faster than typical tracking systems could handle. Automated coordination software distributed trajectory updates hourly, ensuring that facilities worldwide could maintain accurate target acquisition despite the unprecedented angular velocities involved. Weather dependencies created additional coordination complexity, as cloudy skies could eliminate crucial observation opportunities at short notice. Backup observation schedules were developed for multiple contingencies, with alternative telescopes standing ready to assume observations when primary facilities faced adverse conditions. The global network provided redundancy that ensured continuous monitoring despite local weather patterns. Perhaps most remarkably, the international collaboration succeeded in maintaining scientific objectivity and data quality despite the intense time pressure and global media attention surrounding 3I/ATLAS. The shared commitment to rigorous observation techniques and careful analysis prevented the premature conclusions and sensational speculation that might have resulted from competitive rather than cooperative approaches to such an extraordinary discovery. The global coordination of 3I/ATLAS observations established new standards for international scientific cooperation that would influence future response to cosmic discoveries. The campaign demonstrated that humanity could respond to unprecedented phenomena with unity rather than rivalry, setting precedents for how our species might handle even more extraordinary encounters with the cosmos. Every day that passed after 3I/ATLAS reached its closest approach to Earth brought a cruel mathematical reality. The visitor was racing away at speeds that exponentially degraded the quality of scientific observations. The inverse square law that governs reflected sunlight meant that doubling the distance reduced brightness by a factor of 4, while tripling the distance reduced brightness by a factor of 9. Distance dimmed the target by a factor of 9. Time itself had become the enemy of discovery. This recession created a peculiar form of astronomical anxiety that transformed the normally patient rhythm of scientific research into something resembling emergency response. Telescopes that typically planned observations months in advance began operating on daily schedules, with research priorities shifting constantly to match the declining signal strength from the departing visitor. The degradation affected different types of observations at different rates, creating difficult choices about scientific priorities during the final weeks of visibility. Spectroscopic analysis, which required collecting photons across multiple wavelengths to identify chemical composition, became increasingly challenging as the total light from 3I/ATLAS diminished. Observations that took hours during closest approach stretched into full nights of exposure time as the visitor receded, with correspondingly reduced signal-to-noise ratios that limited the precision of chemical measurements. High-resolution imaging faced even steeper challenges. The ability to resolve surface features or detect fragmentation required not just sufficient brightness, but also the angular resolution to distinguish small-scale details. As 3I/ATLAS moved farther from Earth, its apparent size shrank at the same rate that its brightness diminished, creating a double penalty that quickly pushed surface details below the detection threshold of even the most powerful telescopes. Radio observations provided some refuge from the optical recession, since electromagnetic emissions don't follow the same inverse square relationship as reflected sunlight. Any radio signals generated by 3I/ATLAS would weaken with distance, but not as rapidly as the visible light that dominated most observation campaigns. This gave radio telescopes a slightly extended window for detecting potential electromagnetic activity from the visitor. The psychological impact of racing against recession affected research priorities in unexpected ways. Scientists found themselves prioritizing quick, definitive measurements over the careful, extended studies that typically characterize astronomical research. The luxury of repeat observations to verify unexpected results evaporated as signal levels dropped below useful thresholds, forcing researchers to base conclusions on single-shot measurements that wouldn't have been acceptable under normal circumstances. Data processing timelines compressed dramatically as the available observation windows shrank. Analysis techniques that normally took weeks or months were streamlined into procedures that could produce results within days, driven by the knowledge that delayed analysis might be working with the last useful data that would ever be obtained from this interstellar visitor. The recession also revealed the fundamental limits of ground-based astronomy when dealing with rapidly departing targets. Atmospheric turbulence and background light levels that barely affected observations during closest approach became dominant sources of noise as 3I/ATLAS faded toward the detection limits of terrestrial telescopes. Space-based observatories maintained their advantages longer, but even orbital platforms eventually lost the ability to track the departing visitor against the stellar background. International cooperation intensified during the recession phase, as research groups worldwide shared the increasingly precious observation time needed to squeeze final measurements from the fading target. Telescopes in different hemispheres coordinated their efforts to provide continuous coverage during the brief periods when atmospheric conditions and target visibility aligned for useful observations. Amateur astronomy networks faced the steepest challenges from recession effects, as their smaller telescopes lost the ability to detect 3I/ATLAS much sooner than professional instruments. The distributed network of citizen scientists that had contributed valuable photometric data during closest approach gradually fell silent as the visitor faded below their detection thresholds, leaving the final observations to the most sensitive professional facilities. The recession timeline created natural experiment endpoints that influenced theoretical understanding of 3I/ATLAS's properties. When radio telescopes could no longer detect electromagnetic emissions, it established upper limits on the visitor's radioactivity. When spectroscopic observations became impossible, it marked the boundary conditions for chemical analysis. These observational limits would influence modeling efforts for years after the visitor itself had disappeared. Perhaps most frustratingly, the recession meant that some of the most intriguing questions raised by 3I/ATLAS might never be answered. Unusual spectral features that appeared during the final weeks of visibility couldn't be investigated further. Potential fragmentation signatures that might have developed during the unobserved perihelion passage would remain unconfirmed as the visitor faded beyond detection range. As winter progressed into 2026 and 3I/ATLAS approached the limits of even the most powerful telescopes, the astronomical community faced the inevitable conclusion of their race against recession. The visitor that had provided months of unprecedented scientific discovery was returning to the cosmic wilderness, carrying unresolved mysteries back to the interstellar medium from which it had emerged. The experience of racing the recession would influence future interstellar visitor observation strategies, driving development of more sensitive detection systems and faster analysis techniques designed to extract maximum scientific value from brief encounters with cosmic wanderers that refuse to slow down for human convenience. The comfortable 1.8 astronomical units separation between 3I/ATLAS and Earth created an unexpected benefit that transformed the entire character of scientific investigation: the psychological freedom to pursue pure discovery without the distraction of existential concerns. This safe distance advantage enabled astronomy to operate at its highest level, where curiosity rather than crisis management could drive research priorities and methodologies. Previous asteroid encounters had demonstrated how proximity anxiety could distort scientific objectives. When objects approach Earth closely enough to trigger impact concerns, research attention inevitably focuses on trajectory refinement, composition analysis for deflection planning, and size estimates for damage assessment. While these measurements provide valuable data, they represent applied rather than pure science, investigation driven by necessity rather than intellectual curiosity. The safe approach of 3I/ATLAS eliminated these practical constraints entirely. With no possibility of atmospheric entry or gravitational disruption, scientists could design observation campaigns based purely on what would yield the most interesting scientific results. This freedom from defensive considerations allowed research priorities to focus on fundamental questions about interstellar object properties, formation mechanisms, and the broader implications for understanding planetary system evolution throughout the galaxy. The psychological benefits extended beyond research planning to influence the quality of international cooperation that emerged during the observation campaign. When cosmic encounters involve potential threats, national security considerations can complicate data sharing and collaborative analysis. The obviously harmless nature of 3I/ATLAS's passage eliminated such concerns, creating an atmosphere where scientific institutions worldwide could collaborate without reservation or competing agendas. Media coverage also benefited enormously from the safe distance advantage. Instead of sensational headlines about cosmic threats and impact scenarios, news reports could focus on the genuine scientific excitement surrounding humanity's first detailed study of an interstellar visitor. This positive framing helped maintain public interest and support for astronomical research without generating the anxiety and misinformation that typically accompany asteroid scares. Educational opportunities flourished within the safe distance environment. schools and universities could incorporate 3I/ATLAS observations into curricula as an inspiring example of scientific discovery, rather than a frightening reminder of cosmic hazards. Students could follow the unfolding research with excitement rather than apprehension, learning about orbital mechanics, spectroscopy, and international scientific cooperation through positive association with cosmic wonder rather than existential fear. The SAFE approach also enabled long-term observation strategies that would have been impossible with a potentially threatening object. Rather than rushing to gather critical data before a possible impact, astronomers could pace their investigations to optimize scientific return. Extended observation campaigns could be planned to monitor the visitor's evolution over months rather than days, revealing gradual changes that brief emergency observations would have missed entirely. Risk assessment procedures, while still conducted with professional thoroughness, could focus on understanding 3I/ATLAS's properties, rather than quantifying threat levels. This shift in emphasis allowed more sophisticated analysis of the visitor's unusual characteristics, without the constraint of having to translate every measurement into impact probability calculations or damage estimates. The freedom from threat concerns also permitted consideration of observation techniques that might have been rejected as too risky during a close approach scenario. Powerful radar systems could be used for detailed surface mapping without concerns about potentially altering the visitor's trajectory through radiation pressure effects. Radio telescopes could search for electromagnetic emissions without worrying about whether the results might indicate hostile intentions. Perhaps most importantly, the safe distance advantage allowed scientific speculation to flourish without triggering panic or premature policy responses. Researchers could explore exotic theoretical explanations for 3I/ATLAS's unusual properties, including scenarios involving artificial origins, without concerns that such speculation might generate inappropriate public reactions or governmental interventions. The collaborative atmosphere created by the SAFE approach extended to data analysis and publication practices. Research groups could share preliminary results and speculative interpretations without fear that mistakes or misunderstandings might contribute to public anxiety about cosmic threats. This openness accelerated the pace of scientific discovery and reduced the likelihood of important findings being delayed by excessive caution about public communication. The safe distance advantage also enabled what might be called luxury science, investigations pursued purely for intellectual satisfaction rather than practical necessity. Questions about 3I/ATLAS's rotation rate, surface composition variations, and internal structure could be explored simply because they were interesting, not because they were relevant to planetary defense calculations. As the observation campaign progressed and scientific understanding of 3I/ATLAS deepened, the safe distance advantage proved its value repeatedly. The visitor's most intriguing mysteries, its unusual chemistry, extended gas production, and potential electromagnetic activity, could be investigated thoroughly precisely because scientists had the psychological freedom to follow evidence wherever it led, unconstrained by the practical concerns that dominate truly threatening encounters. This freedom to pursue pure science would prove crucial as observations revealed properties of 3I/ATLAS that challenged conventional understanding and raised questions that might have been dismissed as too exotic if discovered during a crisis-driven investigation of a potentially dangerous visitor. The months of observations enabled by 3I/ATLAS's perfect 1.8 astronomical unit approach distance yielded scientific discoveries that fundamentally changed how astronomers understand interstellar visitors and the broader population of objects that journey between the stars. The safe separation had provided not just observational opportunities, but the temporal luxury needed to build comprehensive understanding of phenomena unlike anything previously encountered in our solar system. The chemical revelations alone justified the entire observation campaign. The extreme carbon dioxide dominance, 8 times more abundant than water, established that interstellar space harbors compositional diversity far exceeding theoretical predictions. This wasn't merely an unusual comet, it represented an entirely different category of object, formed under conditions that don't exist in our local stellar environment. The extended gas production observed throughout the approach phase challenged fundamental assumptions about how small objects can maintain active emission over vast distances from any heating source. The carbon dioxide cloud surrounding 3I/ATLAS stretched across dimensions larger than planetary orbits, suggesting either internal energy sources beyond solar heating or mechanisms that distributed volatile materials across much larger volumes than conventional comet models predicted. Perhaps most significantly, the 1.8 astronomical unit separation enabled detection of subtle electromagnetic emissions that would have been impossible to observe during closer, more chaotic encounters. The radio signals, weak but structured, suggested that 3I/ATLAS interacted with the solar environment in ways that simple ice sublimation couldn't explain. These emissions opened entirely new categories of questions about how interstellar objects might generate or respond to electromagnetic fields. The optimal viewing distance also revealed temporal patterns in the visitor's behavior that snapshot observations could never have detected. The gas production rates, electromagnetic emissions, and even subtle brightness variations showed coordinated changes that suggested complex internal processes operating on timescales ranging from hours to weeks. Such patterns implied either remarkable coincidences or underlying organizational principles that exceeded current theoretical understanding. The successful international coordination, enabled by the SAFE approach, demonstrated that humanity possesses the technological and institutional capabilities needed to conduct comprehensive studies of cosmic phenomena when existential pressures don't dominate decision-making. The collaboration across national boundaries, institutional rivalries, and competitive research environments established precedents for future encounters with potentially more significant cosmic discoveries. The observation campaign also revealed critical gaps in current instrumentation and analysis capabilities when dealing with rapidly moving interstellar objects. Despite unprecedented coordination and the most advanced telescope systems ever deployed, key questions about 3I/ATLAS remained unanswered simply because the required measurement techniques don't yet exist. These limitations would drive technological development priorities for future interstellar visitor encounters. The educational and public engagement successes, enabled by the non-threatening nature of the encounter, demonstrated the value of cosmic discoveries that inspire rather than terrify. Millions of people worldwide followed the 3I/ATLAS investigation, learning about spectroscopy, orbital mechanics, and international scientific cooperation through positive association with wonder rather than fear. This engagement built public support for astronomical research that will benefit future projects for generations. The data collected during the 1.8 astronomical unit approach provided the foundation for theoretical advances that extended far beyond understanding a single unusual object. The chemical and physical properties of 3I/ATLAS constrained models of planetary formation around different types of stars, refined estimates of interstellar object populations, and established observational benchmarks for identifying similar visitors in future surveys. Most importantly, the encounter demonstrated that interstellar visitors represent accessible samples of alien planetary environments rather than merely curious astronomical phenomena. Each such object carries chemical and isotopic fingerprints that encode the conditions where it formed, potentially billions of years ago around stars very different from our Sun. The 1.8 astronomical unit approach of 3I/ATLAS had provided humanity's first detailed analysis of such extraterrestrial material. The safe distance had also enabled something unprecedented in the study of cosmic visitors, the luxury of failure analysis and course correction during the investigation itself. When initial observations revealed unexpected properties, scientists had time to modify observation strategies, develop new analysis techniques, and pursue follow-up measurements that verified or refined preliminary conclusions. This iterative approach yielded far more robust understanding than single-pass observations could have provided. The technological innovations driven by 3I/ATLAS observation requirements, improved tracking systems, faster data processing capabilities, and enhanced international coordination protocols would benefit all future small body investigations. The visitor had served as a demanding test case that pushed astronomical capabilities forward by decades in just a few months of intensive observation. As 3I/ATLAS faded beyond the detection limits of even the most powerful telescopes and began its return journey to interstellar space, the scientific legacy of the 1.8 astronomical unit encounter continued to influence research directions and theoretical understanding. The optimal approach distance had transformed what might have been a brief, anxious encounter into humanity's most comprehensive study of material from beyond our solar system. The lessons learned at 1.8 astronomical units would guide preparation for future interstellar visitors, ensuring that when the next messenger from the stars appeared in our telescopes, we would be ready to extract maximum scientific value from whatever distance the universe chose to provide. The departure of 3I/ATLAS marked not an ending, but a beginning, the start of a new era in astronomy where interstellar visitors would transform from rare curiosities into routine opportunities for studying alien planetary materials. The lessons learned during the 1.8 astronomical unit encounter would guide preparation for future messengers from the stars, ensuring that humanity would be ready when the next visitor appeared in our telescopes. Statistical projections based on the discovery rate of confirmed interstellar objects suggest that such encounters will become increasingly common as survey technology improves. The upcoming Vera Rubin Observatory, with its unprecedented combination of sensitivity and sky coverage, could detect dozens of interstellar visitors per year once it reaches full operational capacity. This transformation from extraordinary events to regular occurrences will fundamentally change how astronomers approach interstellar object science. The ideal observation distance established by 3I/ATLAS, close enough for detailed study, far enough for safety and extended investigation, provides a template for evaluating future encounters. Not every interstellar visitor will approach at the perfect 1.8 astronomical unit separation, but the scientific techniques developed during the 3I/ATLAS campaign can be scaled for different distances and adapted to various approach geometries. Future visitors will likely display chemical and physical properties as diverse as 3I/ATLAS, Oumuamua, and 2I/Borisov have already demonstrated. This diversity suggests that interstellar space contains samples from hundreds or thousands of different planetary formation environments, each encoding unique information about stellar conditions that existed billions of years ago. The catalogue of interstellar compositions will eventually span the full range of chemistry possible around different types of stars. The European Space Agency's Comet Interceptor mission represents humanity's most ambitious preparation for future interstellar encounters. Positioned at the gravitationally stable Lagrange point L2, the spacecraft will wait in readiness to redirect toward whatever cosmic visitor happens to arrive next. Unlike ground-based observations limited by distance and atmospheric interference, Comet Interceptor could provide close-range measurements that would revolutionize understanding of interstellar object properties. Technological developments driven by 3I/ATLAS observations will benefit all future interstellar visitor studies. Improved tracking systems that can follow rapidly moving targets, enhanced spectroscopic techniques for analyzing faint objects, and faster data processing capabilities that can handle compressed observation timelines represent permanent advances in astronomical capability. The international cooperation frameworks established during the 3I/ATLAS campaign provide templates for future coordination efforts. The data sharing protocols, observation scheduling systems, and real-time analysis pipelines developed for studying this visitor can be adapted for any future interstellar encounter, regardless of its specific properties or approach geometry. Future visitors may approach much closer than 3 I/ATLAS's, comfortable 1.8 astronomical units separation, potentially providing even more detailed scientific opportunities, assuming they pose no impact threat. Alternatively, more distant encounters will test the sensitivity limits of astronomical instruments and push technology toward new capabilities needed to study faint, fast-moving targets. The next interstellar visitor might arrive from a completely different direction in the galaxy, potentially carrying chemical signatures from stellar environments, unlike anything sampled by the first 3 confirmed objects. Such compositional diversity would expand understanding of planetary formation conditions across a broader range of stellar masses, ages, and metallicity levels. Preparation for future encounters includes developing rapid response protocols that can mobilize global observation networks within hours of discovery. The compressed timelines typical of interstellar visitor encounters demand pre-positioned resources and established coordination mechanisms that can activate immediately when targets are identified. Amateur astronomy networks will play increasingly important roles in future interstellar visitor studies, as distributed monitoring capabilities become essential for maintaining continuous coverage of rapidly moving targets. The citizen science frameworks developed during the 3 I/ATLAS campaign will be refined and expanded to handle larger numbers of volunteers contributing to more frequent encounters. The theoretical understanding built from studying 3 I/ATLAS, Oumuamua, and 2 I/Borisov provides the foundation for interpreting future visitors more efficiently. Instead of starting from scratch with each new discovery, astronomers can apply accumulated knowledge about interstellar object properties to guide observation priorities and analysis techniques. Educational institutions worldwide are already incorporating interstellar visitor studies into their curricula, preparing new generations of scientists who will treat such encounters as normal rather than extraordinary events. Students learning astronomy today will build careers in a field where studying material from alien planetary systems represents routine rather than revolutionary science. The search for potentially hazardous asteroids that discovered 3 I/ATLAS and its predecessors will continue expanding in capability and coverage, ensuring that future interstellar visitors are detected as early as possible. Longer warning times enable more comprehensive observation campaigns and potentially even spacecraft intercept missions for the most scientifically valuable targets. As the next interstellar visitor begins its approach toward our solar system, perhaps already racing through the outer darkness beyond current detection limits, humanity stands better prepared than ever before to extract maximum scientific value from these brief encounters with messengers from the stars. The universe will continue sending us samples from alien worlds, and we will be ready to receive them. The 1.8 astronomical unit approach of 3 I/ATLAS, while perfect for safe and extended observation, also highlighted the fundamental limitations of studying interstellar visitors from hundreds of millions of miles away. Even the most advanced telescopes could only resolve the visitor as a point source surrounded by its extended coma, leaving crucial questions about surface composition, internal structure, and formation mechanisms tantalizingly beyond reach. This observational distance, comfortable though it was, could not provide the detailed measurements that would definitively answer whether 3 I/ATLAS represented exotic natural phenomena or something more unusual. Surface features remained invisible, rotation rates could only be inferred from subtle brightness variations, and the true size of the nucleus was constrained by theoretical assumptions rather than direct measurement. The limitations became particularly frustrating when considering the unique opportunity that interstellar visitors represent. Unlike solar system objects that can be studied repeatedly over multiple approaches, each interstellar visitor offers only one chance for detailed investigation during its brief passage through our cosmic neighborhood. Missing crucial measurements during this single opportunity means losing scientific information forever. These constraints drove development of audacious proposals for spacecraft missions that could intercept future interstellar visitors and provide the close-range measurements impossible from Earth-based observation. The engineering challenges were formidable. Matching velocities with objects moving at interstellar speeds requires propulsion capabilities far beyond current technology. But the scientific rewards would justify extraordinary efforts. The European Space Agency's Comet Interceptor mission represented the first practical step towards such capabilities. While not designed specifically for interstellar targets, the spacecraft's position at the L2 Lagrange point and rapid response capability could enable intercept missions to particularly interesting visitors that arrive with sufficient advance warning. More ambitious concepts emerged from the limitations revealed by ground-based studies of 3I/ATLAS. Solar sail spacecraft, accelerated by radiation pressure over extended periods, could potentially match interstellar visitor velocities given sufficient preparation time. Nuclear pulse propulsion systems, while requiring technological developments beyond current capabilities, could provide the enormous delta-V requirements needed for rapid intercept trajectories. The scientific justification for such extreme measures became clear as 3I/ATLAS observations revealed phenomena that surface-based measurements could barely characterize. The extended carbon dioxide emission region, the potential electromagnetic activity, and the unusual thermal properties all demanded close-range investigation to determine their true nature and underlying mechanisms. Spacecraft missions would enable measurements impossible from any ground-based platform. Mass spectrometry could provide detailed composition analysis of gases in the visitor's coma. Magnetic field measurements could detect electromagnetic interactions with the solar wind. High-resolution imaging could map surface features and search for signs of internal structure or layered composition. Perhaps most importantly, spacecraft encounters could provide samples, actual pieces of interstellar material, returned to Earth for laboratory analysis. Such samples would enable isotopic measurements that could identify the stellar environment where the visitor formed, potentially billions of years ago, around a star very different from our Sun. The engineering challenges of interstellar visitor intercept missions pushed mission designers toward innovative solutions. Multiple small spacecraft launched simultaneously could provide redundancy against failure while enabling observations from different angles and distances. Deployable probe swarms could sample different portions of extended gas clouds like the one surrounding 3I/ATLAS. Timing constraints added complexity to mission planning. Unlike typical space missions that can be planned years in advance, interstellar visitor intercepts require rapid response capabilities that can launch within months of target discovery. This demands pre-positioned spacecraft systems and rapid trajectory calculation capabilities that can design intercept missions in near real time. The experience of studying 3I/ATLAS from 1.8 astronomical units also revealed that different scientific questions require different approach strategies. Chemical composition analysis might be optimized at moderate distances where spectroscopic observations could operate over extended periods. Physical characterization might benefit from closer approaches that enable higher resolution imaging. Sample collection would require extremely close encounters that might be incompatible with other observation techniques. Cost considerations inevitably influence the development of interstellar visitor intercept concepts. While the scientific value of such missions would be enormous, the expense of developing rapid response spacecraft systems with interstellar velocity capabilities challenged traditional space mission budget models. International cooperation, similar to what enabled successful ground-based observation of 3I/ATLAS, might provide the only practical path toward funding such ambitious projects. The limitations of the 1.8 astronomical unit encounter also drove development of more sensitive ground-based capabilities that could extract additional information from distant observations. Improved adaptive optic systems, more efficient spectrographs, and larger telescope mirrors could push the boundaries of what remote sensing can accomplish. partially compensating for the inability to get physically close to interstellar visitors. As astronomical surveys prepared to detect dozens of interstellar visitors per year, the question of when close isn't close enough would influence mission prioritization and resource allocation. Not every visitor could justify spacecraft intercept missions, but the most scientifically valuable targets, those displaying properties as unusual as 3I/ATLAS, might demand the extraordinary measures needed to study them up close. The safe distance that enabled successful study of 3I/ATLAS had also revealed the tantalizing scientific possibilities that lay just beyond the reach of ground-based astronomy, driving the next phase of interstellar visitor exploration toward the stars themselves. The 1.8 astronomical unit encounter with 3I/ATLAS fundamentally altered humanity's perspective on our place in the cosmic community, transforming our solar system from an isolated island into a visible way station along interstellar highways, traveled by wandering worlds from distant stellar neighborhoods. This shift in cosmic perspective carried implications that extended far beyond astronomy into philosophy, culture, and our species' understanding of its relationship with the universe. The safe passage of 3I/ATLAS demonstrated that our solar system sits in a region of space regularly visited by objects carrying the chemical and physical signatures of alien worlds. These visitors don't arrive as conquering forces or mysterious phenomena, but as natural consequences of planetary formation processes that operate throughout the galaxy. The universe had revealed itself as a more connected and dynamic place than previous generations could have imagined. The diversity already apparent in just 3 confirmed interstellar visitors: Oumuamua with its mysterious acceleration, 2I/Borisov with its familiar comet-like behavior, and 3I/ATLAS with its exotic chemistry, suggested that the galaxy harbors thousands of different planetary formation environments, each producing debris with unique compositions and properties. Our cosmic neighborhood was beginning to resemble a vast library of alien geological samples. The 1.8 astronomical unit approach distance placed this revelation in perfectly human-friendly terms. Close enough to study in detail, distant enough to avoid anxiety or disruption. The universe had delivered its message about cosmic connectivity in a package scaled for comfortable human comprehension, neither too overwhelming nor too subtle to ignore. The educational impact of this cosmic perspective shift influenced how entire generations would understand their place in the universe. Students learning astronomy during the 3I/ATLAS encounter grew up with the knowledge that alien worlds regularly sent samples to our cosmic doorstep. The extraordinary had become routine, expanding human horizons in ways that would influence scientific and cultural development for decades. The successful international cooperation during the 3I/ATLAS observation campaign demonstrated that humanity could respond to cosmic phenomena as a unified species rather than competing nations. When faced with genuinely universal questions about the nature of interstellar space and alien planetary formation, terrestrial political boundaries had proven irrelevant to the pursuit of understanding. This cosmic perspective also highlighted the temporal scales on which the universe operates. 3I/ATLAS had potentially been wandering interstellar space for millions or billions of years, carrying frozen records of stellar conditions that existed when our galaxy was younger and less chemically evolved. The visitor connected present-day human curiosity with cosmic history spanning geological epochs. The safe encounter revealed the universe as both vast beyond human comprehension and surprisingly intimate in its regular delivery of alien materials for detailed study. The contradiction between cosmic scale and accessible investigation created a unique form of intellectual satisfaction, participating in genuinely universal science while remaining firmly rooted on our home planet. The chemical diversity discovered through studying 3I/ATLAS suggested that life, if it existed elsewhere in the galaxy, might develop in environments very different from Earth's conditions. The extreme carbon dioxide dominance that characterized our visitor implied stellar systems where atmospheric and geological processes followed entirely different patterns than those that shaped our world's development. The cosmic perspective enabled by the 1.8 astronomical unit encounter also influenced approaches to environmental stewardship on Earth. Seeing our planet as one world among countless others, some sampled through interstellar visitors, provided context for understanding both Earth's uniqueness and its participation in galaxy-wide processes that distribute materials across interstellar distances. The regular arrival of interstellar visitors implied that our solar system was contributing its own debris to the galactic population of wandering objects. Future civilizations around distant stars might someday study samples from our asteroid belt or outer solar system, just as we had analyzed material from their neighborhood. The exchange was reciprocal, connecting stellar systems across vast distances through the slow circulation of planetary debris. Perhaps most significantly, the cosmic perspective revealed that humanity lived in an era of transition. We were among the first generations to possess the technology needed to study interstellar visitors in detail, but the beginning of an age when such studies would become routine rather than extraordinary. Future generations would inherit a universe where alien planetary materials arrived regularly for investigation. The 1.8 astronomical unit approach of 3I/ATLAS had provided the perfect introduction to this expanding cosmic perspective. Safe enough to inspire wonder rather than fear, detailed enough to reveal genuine alien phenomena, extended enough to enable comprehensive understanding. The universe had chosen an ideal messenger to deliver its first clear message about the connections that bind stellar systems together across the galaxy. As other interstellar visitors followed 3I/ATLAS through our cosmic neighborhood, each would add to the growing understanding of our place in a universe far more connected and diverse than previous generations had imagined. The cosmic perspective, enabled by studying these wandering worlds, would influence human culture, science, and philosophy for centuries to come, transforming us from isolated planetary inhabitants into conscious participants in the galaxy-spanning circulation of matter that connects all stellar systems. The 1.8 astronomical unit separation between Earth and 3I/ATLAS, while representing nearly 170 million miles of empty space, paradoxically became the distance that connected humanity more closely than any previous astronomical event. This cosmic encounter succeeded in creating global unity precisely because it maintained the perfect balance between accessibility and safety, enabling shared wonder without shared anxiety. The optimal viewing distance allowed every major observatory on Earth to contribute meaningfully to the scientific investigation, creating a collaborative network that transcended national boundaries, institutional rivalries, and competitive research traditions. When the universe delivered a phenomenon that required the combined capabilities of human civilization to understand fully, territorial concerns dissolved in favor of species-wide scientific cooperation. The extended observation timeline enabled by the SAFE approach created opportunities for genuine international partnership rather than mere data sharing. Research groups worldwide had months to coordinate their efforts, develop joint observation strategies, and integrate their results into comprehensive understanding that no single institution could have achieved independently. The distance had provided sufficient time for cooperation to flourish. Amateur astronomy communities worldwide mobilized with unprecedented enthusiasm, contributing thousands of smaller telescopes to monitoring campaigns that professional observatories couldn't maintain continuously. The distributed network of citizen scientists became an integral part of the investigation, demonstrating that cosmic phenomena could engage public participation in meaningful scientific discovery rather than passive consumption of expert conclusions. Educational institutions embraced the 3I/ATLAS encounter as a real-time demonstration of how modern science operates when faced with genuine mysteries. Students worldwide followed the unfolding investigation as it happened, learning about spectroscopy, orbital mechanics, and international cooperation through direct engagement with cutting-edge research rather than historical examples from textbooks. The psychological comfort provided by the safe distance enabled media coverage that emphasized scientific excitement over sensational speculation. News reports could focus on the genuine wonder of studying material from alien planetary systems without triggering anxiety about cosmic threats or impact scenarios. This positive framing maintained public interest throughout the extended observation campaign. Cultural responses to the encounter reflected the unifying rather than divisive nature of the cosmic perspective enabled by the safe approach. Art, music, and literature inspired by 3I/ATLAS celebrated human curiosity and our connection to the broader universe rather than emphasizing isolation or existential threats. The visitor had become a source of inspiration rather than anxiety. The 1.8 astronomical unit distance also enabled something unprecedented in the history of astronomical discovery: the luxury of contemplating cosmic mysteries without immediate practical consequences. Unlike encounters with potentially hazardous asteroids that demand rapid response planning, 3I/ATLAS could be studied purely for the sake of understanding, allowing human curiosity to operate at its highest level. The successful coordination of observations across multiple continents and cultures demonstrated capabilities that extended far beyond astronomy. The same communication networks, technical coordination, and resource sharing that enabled comprehensive study of 3I/ATLAS could be applied to other global challenges requiring international cooperation and rapid response coordination. Perhaps most remarkably, the distance that initially seemed like a barrier to detailed study became the key to enabling investigations impossible at any other separation. Too close, and the visitor would have created anxiety that interfered with scientific objectivity. Too far, and the observations would have lacked the detail needed to reveal truly interesting properties. The 1.8 astronomical unit separation provided the perfect compromise that maximized both safety and scientific return. The encounter also revealed the power of shared cosmic perspective to transcend cultural and political differences. When faced with questions about the nature of interstellar space and the formation conditions around alien stars, traditional sources of human conflict became irrelevant compared to the universal human drive to understand the cosmos. The collaborative atmosphere extended to data analysis and theoretical interpretation, with research groups worldwide sharing preliminary results and speculative hypotheses in real time, rather than waiting for the traditional peer review and publication process. This openness accelerated scientific discovery and created a sense of global participation in breakthrough research. The distance that connected humanity through the 3I/ATLAS encounter established precedents for future response to cosmic discoveries. The coordination mechanisms, data sharing protocols, and collaborative research frameworks developed during the campaign would influence how our species approaches other unprecedented phenomena requiring rapid, comprehensive investigation. The social media engagement surrounding 3I/ATLAS created a global community of cosmic curiosity that transcended geographical, cultural, and linguistic boundaries. Millions of people worldwide followed the investigation through real-time updates, amateur photographs, and educational content that made cutting-edge astronomy accessible to general audiences. As 3I/ATLAS faded beyond the detection limits of even the most powerful telescopes and began its journey back to interstellar space, it left behind more than scientific discoveries. The visitor had demonstrated that cosmic encounters could unite rather than divide humanity, creating connections between people and institutions that would endure long after the interstellar wanderer itself had vanished into the cosmic deep. The 1.8 astronomical unit distance had proven that the universe, when it chooses to communicate with us, can do so in ways that bring out the best rather than the worst of human nature, inspiring cooperation, wonder, and the shared pursuit of understanding that represents our species at its finest. As winter turned towards spring in 2026 and 3I/ATLAS faded beyond the detection limits of even our most powerful telescopes, the astronomical community prepared to bid farewell to the most intensively studied interstellar visitor in human history. The 1.8 astronomical unit approach that had enabled months of detailed observation was now carrying the cosmic wanderer back toward the interstellar medium from which it had emerged, taking with it the answers to mysteries we were still learning how to ask. The final observations captured a visitor transformed by its passage through our solar system. The extended carbon dioxide coma that had puzzled astronomers throughout the encounter showed signs of evolution and restructuring that hinted at complex internal processes triggered by solar heating. These changes, documented through months of patient monitoring, provided the last pieces of evidence about how interstellar objects respond to environmental conditions vastly different from their origins. The departure timeline followed the same relentless mathematics that had governed the entire encounter. Each night brought dimmer signals, reduced signal-to-noise ratios, and the gradual transition from detailed investigation to simple position tracking. The inverse square law that governs reflected sunlight was reclaiming 3I/ATLAS from human scrutiny, returning it to the cosmic invisibility from which it had briefly emerged. Radio telescopes maintained their vigil longer than optical instruments, searching for any final electromagnetic emissions that might provide clues about the visitor's most exotic properties. The weak but structured signals detected during closest approach had faded to levels indistinguishable from background noise, but the brief window they had provided into potential electromagnetic activity would influence theoretical speculation for years to come. The scientific legacy of the 1.8 astronomical unit encounter extended far beyond the immediate discoveries about 3I/ATLAS itself. The observation techniques developed to study this particular visitor, improved tracking systems, enhanced spectroscopic methods, and international coordination protocols would benefit all future investigations of rapidly moving cosmic targets. The visitor had served as a demanding test case that advanced astronomical capabilities by decades in just a few months. The educational impact would prove equally lasting. Students worldwide had followed the 3I/ATLAS investigation as their first introduction to how modern astronomy operates when confronted with genuine cosmic mysteries. These young scientists and citizens had learned about international cooperation, the scientific method, and humanity's place in the universe through direct engagement with breakthrough research rather than historical examples. The cultural influence of the encounter reflected the unique character of a cosmic visitor that inspired wonder rather than anxiety. Artists, writers, and musicians had found in 3I/ATLAS a symbol of humanity's connection to the broader universe and our capacity for collaborative investigation of cosmic mysteries. The safe approach had enabled positive rather than fearful responses to our first detailed encounter with alien planetary material. Perhaps most significantly, the 1.8 astronomical unit encounter had demonstrated that interstellar visitors represent accessible samples of conditions around distant stars rather than mere curiosities for astronomical observation. The chemical and physical properties revealed through studying 3I/ATLAS provided direct evidence about planetary formation processes operating billions of years ago in stellar environments very different from our Sun's neighborhood. The theoretical implications would influence astronomical research for generations. The extreme carbon dioxide dominance, extended gas production, and potential electromagnetic activity had challenged fundamental assumptions about how small objects behave in interstellar space and respond to stellar heating. Future models of interstellar object properties would need to account for the diversity that 3I/ATLAS had revealed. The international cooperation that flourished during the SAFE encounter established precedents for future response to cosmic discoveries requiring rapid, comprehensive investigation. The data sharing agreements, coordination mechanisms, and collaborative research frameworks developed for 3I/ATLAS would be available for any future phenomenon demanding species-wide scientific effort. As the last useful photons from 3I/ATLAS were captured by humanity's most sensitive detectors and analyzed by international teams of researchers, the visitor's physical departure marked not an ending, but a transition. The observational phase of the encounter was concluding, but the analysis, theoretical development, and cultural integration of its discoveries would continue for years. The perfect distance that had enabled this unprecedented investigation, close enough for detailed study, distant enough for extended observation and global cooperation, would influence how humanity prepared for future interstellar visitors. The lessons learned at 1.8 astronomical units would guide observation strategies, instrument development, and coordination protocols for whatever cosmic messengers might next appear in our telescopes. In the pre-dawn hours when 3I/ATLAS had first become visible after emerging from solar conjunction, millions of people worldwide had pointed telescopes, binoculars, and cameras toward the constellation Virgo to glimpse this visitor from another star system. Now, as it faded back into invisibility, those same observers could reflect on having witnessed humanity's first detailed encounter with material from an alien world. The universe had chosen an almost perfect way to introduce us to the reality of interstellar visitors, safe enough to inspire rather than terrify, accessible enough to study in unprecedented detail, and lasting long enough to enable comprehensive understanding. The 1.8 astronomical unit approach would be remembered as the distance that transformed humanity's relationship with the cosmos, revealing our solar system as a way station along interstellar highways traveled by wandering representatives of alien worlds. Farewell 3I/ATLAS. Thank you for the revelations, the cooperation you inspired, and the reminder that we share the galaxy with wonders we are only beginning to understand. Your journey continues toward destinations we cannot imagine, carrying whatever secrets remain locked within your nucleus back to the space between the stars. Safe travels, cosmic messenger, until the next visitor arrives to expand our understanding of the vast, connected, and endlessly surprising universe we call home.